Welcome back to another episode. This is going to be a continuation of what we started a couple of days ago, covering the first day of AMD Instinct GPU training. This episode, on the other hand, is going to be focusing on the second day. Unfortunately, we have only access to AMD cluster until tomorrow midnight, so more than likely I can't cover day 3 and day 4 in time. And if I am not going to have access to this AMD cluster, then probably there's no point in making these wrap ups because the presentations, the talks, and everything you can find through HLRS Supercomputing Center, the website, and even some other places they have events. AMD has events similar to this. So the only reason that we are doing this is because that we can compile and run the code on these MI300A devices. So that basically remains to be seen. I do my best um, until tomorrow midnight, but I make no promises. Um, that's the first thing I want to say. Before jumping into the material of this episode, the acknowledgement is the same. HLRS Supercomputing Center and AMD for providing such an amazing training session. And the disclaimers are also the same. So whatever I say here is neither supported nor endorsed by neither of the institutes, neither of HLRS nor AMD. And I might make a lot of mistakes during the talk. And then if you're a veteran, please correct me, educate me. And the other disclaimer is that if you see like performance numbers here, please do not consider them as the baseline because the system is basically shared between a gajillion amount of people. So yeah. So now on day one, we basically viewed APU as a hardware design and then the philosophy that comes with it as APU programming model. And then we try to look at using OpenMP or these pragma-based languages such as OpenMP to port our CPU code to GPUs. And then we saw basically two configurations. One was with APU programming model and the other one suitable for discrete GPUs. And then on second day, we basically did the same thing. We went to the same direction, but this time we changed the programming language to HIP. So, what is HIP? It's basically a fancy name, heterogeneous interface for portability. But the idea is quite simple. It's just a series of C++ runtime API calls, and then maybe you can consider it also as a kernel language. So, yeah, that's basically it. So just like any other library, you just include it in your source code and then you try to use it. For example, with some special qualifiers, you can say that, hey, this function is a kernel function, or then with that triple chevron syntax or these triple angular brackets, you can say that, hey, launch this kernel, and so on and so forth. So just like a previous episode, I only picked a handful amount of slides. So this is from the first talk by Giacomo, and it was about like hip and rock'em, as you can see from the top up here. This is an example, as I said. You include this header file, this hip runtime, and then you see this one is something new, probably to us. We haven't seen this before. So this global basically means that this is an entry point to a kernel function, and it's going to be launched from the host. That's what it means basically. And then the void is the return type. So kernels cannot have any return value, so that's why we have void here. And then this is something that probably also we haven't seen. So this is how we can calculate the global ID of a thread. And if you're familiar with NVIDIA, these keywords are exactly the same as what NVIDIA uses to have sort of the same frame and not having confusion between different sort of programming languages. And yeah, And usually, so block dimension is basically the number of threads that you have in a block. Block index is the index of the block that you have in your grid, and thread index is actually the index of the local index of your thread within your block. Then we usually have this if condition, because not always the size of the array is going to be exactly equal to the number of unleashed threads. And we don't want to have access to regions of the memory that doesn't belong to us. So that's why we put this condition always there. So this multiply function is very similar. It's just multiplying every element by 2. That we have the size of the array, and then we have the size in bytes. That's n times the size of double. And then we allocate memory with the help of malloc on the host, and this h basically corresponds to host. Then we initialize that host array, and then what we do is that we create a device pointer. That's d corresponds to device. And then this is the first sort of HIP API call. This is HIP malloc. And then you pass in the device pointer that you allocated, and then the number of bytes. So this is going to allocate memory on the device. And then we have a HIP mem copy that basically takes the values of host array A and then copies them into device array A. And then with the same amount of bytes, and then this is the direction from host to device. And then we have a sort of number of threads per block, 256. It should be a multiplier of 64. Then the blocks in grid are going to be the ceiling function of n, the size of the array, divided by the threads per block, divided by 256. And then there's the same notation as these triple angular brackets. Then you give the number of blocks in the grid and then the threads in the block, and you pass in the function arguments. And if you are working on APU programming models, then instead of the device version of A, you can basically send HA, and also notice that there's going to be no nonsense business like these memory HIP malloc and HIP mem copy, and also this HIP mem copy from device to host. There's going to be no sign of these stuff if you are doing APU programming model. Yeah. So that is basically it. And then after, so this is the point that, as I said, from device to host the direction, and then it puts the resulting values on DA to HA on the host again. And then you need to also always clean up after yourself, because these were allocated on heap memory. Then you need to free them. So this is the corresponding call to malloc, and heap free is the corresponding API call to HIP malloc to free the resources on the device side. So that is as simple as that. And then in one slide, basically, we saw that with APU programming model, we don't need any of this crap. And this could be also replaced with HA. And we are basically having the same unified shared memory. And yeah, this is in a nutshell whatever you need to do with HIP. You need to include this file. You need to specify with some qualifiers the kernel functions, and if necessary, if you are programming for discrete GPUs, you need to manage the memory yourself. Otherwise, it's just as simple as launching the kernel and then synchronizing the device. This is also important. HIP mem copy already basically blocks. And yeah, so after this, the subjects that we discussed was that the GPU kernels are also asynchronous with respect to the host. So this means that after the host launches the kernel, then it basically continues to do further instructions down the road. That's what it means. And then we said that there are like two configurations or two scenarios. The one scenario is that imagine that like the number of the size of the array is like 30 elements, and then you you can unleash 30 threads that every thread is going to be dealing with one element of the array. Or that was the first case. The second scenario is where you can sort of unleash a fixed amount of threads, and then those threads are going to work on multiple elements on that array. For example, on an array of size 30, then you can have, for example, you can unleash 10 threads, and then thread, for example, 1 is going to be responsible for index 0, and then everything is going to be shifted with the size of the stride, and that is going to be the size of, or the number of threads that you have in your system. Then it's going to be like index 0, and then plus 10, index 10, and then plus 10, index 20, and then plus 10 is going to be 30, which for the size of 30, we have indices from 0 to 29. So thread 1 only works on 3 data elements, index 0, index 10, and index 20. And so on and so forth. Every thread is going to be shifted once working on the data. That's it. And we had error checking mechanisms. We said part of the errors are coming from API calls. They could come from API calls, and that is here it's not shown, but usually these HIP API calls are wrapped around another macro. We showed in the previous wrap up on day 1. Part of the HIP codes, they had a small macro, if you remember, that wraps up these calls to HIP API calls. But part of the errors are also coming from the kernel, and kernel has 2 aspects. The first aspect is on the launch of the kernel. For example, if you pass in invalid arguments, and part of the errors are happening because of or during the kernel execution. So the first category of the errors are called synchronous errors. They're happening on the launch of the kernel. For example, due to an invalid argument. And in order to figure out those errors, you can use this HIP get last error, I think, that HIP API call. And for asynchronous errors, the second category of the errors that they are happening during the execution of the kernel. For example, it could be like some threads accessing the memory that it doesn't belong to them, or stuff of that nature, for example. Then you need to use a synchronize point, something like HIP device synchronize, if I remember correctly. That's it. And then we have, for example, we talked about different versions of this HIP mem copy. Like this is basically blocking the host, and because you need to promise that the HA that you are sending to copy over DA, meanwhile that this HIP mem copy is running, if it was asynchronous, then meanwhile that this HIP mem copy is running, the host could basically change this HA in some instructions down the road, and then there is no guarantee that this HIP mem copy is going to work. Then that is why this call is blocking to the host as well, to make sure that the memory that we are copying is not getting altered in any way. But we do have option of like pinning the memory. I think it was like HIP host mem copy, something like that. Yeah, and then you can consequently use also, instead of HIP, sorry, my bad. It wasn't HIP mem copy. It was HIP malloc. So you can basically allocate a pinned memory, and that was HIP host malloc. And yeah, and then the corresponding HIP mem copy could be exchanged with HIP mem copy async. That's the asynchronous mode. Yeah, but then if you want to use the values within that memory, then you need to make sure that you synchronize first to make sure that everything is fine and the data is safely accessible. Yeah, that is another point that we discussed. And then we talked about the idea of streams. Of course, streams are simply a set of tasks that you can have. It could be like kernel execution. It could be copying data from host to device, copying data from device to host, or any kind of task. So you can have different streams or different sets of these tasks aligned. And Yeah, and these tasks could be running concurrently, and they can also share resources. But again, this is your responsibility as a programmer to make sure that you are not accessing the same memory, or you are not making any race conditions, and so on and so forth. Then we talked about like device management, that the API also provides some calls like, I don't know, hip get device, hip set device, hip get device props, and stuff like that, in cases that you are having like multiple GPUs, or you are having multiple processes, and you are having different ranks in your system with MPI. I'm sorry. Then we also talked about some function qualifiers, for example, things similar to global. As we said, this is an entry point. This means that it's an entry point to a kernel function, and it's going to be a launch from the host. Another version is device, like underscore underscore device, and then underscore underscore. And that means basically it could be only residing within a global kernel, a global region, or it could be called from within another device function. And it's basically not going to be compiled for the host code. It's only going to be compiled for the device, and it's going to execute on the device only. Another variant was host device, that basically could be within a global block, and in that case, it's going to execute on the device. It could be on another device function. Again, it's going to execute on a device. It could be also on the host function, on not in a kernel function, in any other function, and that way it's going to execute on the host. Yeah, and then we had also a few words on threads themselves. Like we said, within a kernel, you are not allowed to have dynamic memory allocation. Memory can be only acquired from the stack. The variables can be defined on the stack. I'm sorry. And the variables that are defined on the stack are private to every thread, and every thread has its own version, and it's not shared between anybody else, unless if you use this is specifier underscore underscore share this underscore underscore. Then in that case, all the threads within the same block, only the threads within the same block are going to have access to the same variable. That was it. And in the second talk, we basically talked about, let me find it. I think it was this one. Yeah. Second talk was again by Giacomo, and it was about porting the code to heap from CPU to GPU. And then in this talk, they introduced a bunch of tools that we can use, like Hippify Perl and Hippify Clang. Hippify Perl is a very simple tool, just find and replace. A more robust tool is going to be Hippify Clang. Then again, in the end, we said that probably a combination of like usage of Hippify Clang and then doing some manual hip coding is going to be necessary in complex cases where you have like an already existing CUDA code, which uses like very special and very complex functions, because not every API call on NVIDIA side is going to have an equivalent on the hip side. Yeah. And then we said another tool to use is Hippify, the one that you see on this slide, for example. And this one is a little bit different. It has a header file, and this within this header file, with the help of macros, you are basically mapping every call on CUDA. For example, this CUDA error, there's the hip error T. So it basically uses macros. And within your project, with certain flags, you can simply in your build system add on the fly. Once the compilation is happening, you can change the code either to run on NVIDIA or to run on HIP. So this is another way of doing things. And after this, either you are using Hippify or you're using Hippify Perl or Hippify Clang. All of these tools cannot change sort of the make file or the CMake if you are using. They cannot change your build system. Still, as a programmer, it's your responsibility to change your build system accordingly. Yeah, this is basically all we talked about in the second talk. And in the third talk, it was presented by Johanna, and we had, let me check, it was a talk about interoperability. The question is basically, can we use OpenMP and HIP at the same time in the same sort of source code? And then the answer is absolutely yes, but there is a caveat, or there is like a trick that you need to do. And the thing is that the OpenMP code needs to be in a separate translation unit compared to this HIP code. That was the only trick, because, and the reason for that is because simply this one is going to be compiled with HipCC, and this code is going to be compiled for compiled with Clang. And then on the OpenMP side, because this side is written on HIP, and these sort of things, these pointers are device pointers. They should be device pointers. So that is why on the OpenMP side, we use this pragma-OMP target data use device pointer, because we want to basically send X and Y, and these X and Y needs to be device pointers. Yeah, that's how you basically um, do basically interoperability of OpenMP and HIP. Yeah, we can see a bunch of examples on this one as well. So that was a quick wrap up of the 3 talks that we had. Unfortunately, I had a meeting and I couldn't basically audit the last talk of which was presented by Gina, and that was about optimization of HIP. Yeah, hopefully I can listen to that after the recordings are being available by HLRS. So now I'm on the AMD cluster, the accelerated AMD cloud, and let's take a look at a bunch of examples. We can start with HIP. That was the first thing. Let's go with vector. I think this is part of the examples that we needed to do. Let's take a look at README here. So here it says for ROCm environments, you need to say module load ROCm, module load CMake, and if you are having CMake, of course. If you want to use make, simply just make. So it doesn't seem like we have anything special here. So let's take a look at the vector add HIP. First things to notice is that we have this ndebug here. If defined ndebug, there's going to be no debugging available. Then this macro simply says that wherever you see a HIP assert with an X in between, then simply substitute that with the X itself. So if I have ndebug, that means no debugging, then HIP assert calls are going to be just out of the window. We're going to have only the X, whatever call from the API that is. Else, if I have the debug, then HIP assert X is going to be substituted with assert of X, whether it's equal to be HIP success. So we're going to call that basically HIP API, and then we're going to compare the return value of that call to HIP success. And if it's basically equal, then it's going to be fine. If not, then assert is going to basically throw you an error. Then in this case, we have width and height as 1024. The total number is going to be that multiplication, threads per block. So it seems like we are having a two-dimensional array here, a two-dimensional sort of grid of threads. And yeah, so this is a vector add, and you see that we are accessing X and Y through the block dimensions, the same way that I was talking about earlier to calculate the global ID, but we need to do it once for rows and once for columns. And then simply you basically flatten it, you linearize it, so that's Y multiplied by width plus X, and that's going to be your index, because the arrays that we are working, they are not two-dimensional. So that's why we need to make this index sort of a linear index depending on the rows and the columns. And then we check whether this index is less than width times height, and understandably so, because we don't want to allocate, we don't want to access the memory that is not ours. And then it simply sums up B and C, and then it puts the result into A. That's the kernel function. And then you see that we allocate some stuff. We have the pointers for host and device, and then later we need to allocate probably. So this is one of those device management stuff I was talking about, hip device prop T, for example. And then it basically dumps out some information about the device through this minor, major, and name. And then we allocate stuff with malloc for the host. And then we initialize only B and C, because A, it doesn't matter what initial values it has. And the way that we are initializing is that this is going to be equal to the loop counter, and this one is going to multiply by 100. So the first one is going to be like 0 and 0, and then the next one is going to be 1 and then 100, and then the next one is going to be 2 and 200, and so on and so forth. And then we have for the device, we're using this hip malloc, and then again you see that we wrap it in this hip assert that we saw earlier on top. Whether we are having ndebug on or not, it's gonna basically change. And then we have hip mem copy. Of course, we have only 2 calls of this because we need to send the host values of B and C. It doesn't matter what values A holds, because A is going to be filled up on the device after this kernel function is running. This is sort of another way of calling kernels or launching kernels, but we are not using this. This is commented out, and then we have the grid, and then we construct the blocks, and then the vector add is going to be launched with this grid, and then this block, and a 0 shared memory, and on the null stream as well. Then after this launch of the kernel, we want to basically copy the values on the device to the host, and we're going to check whether this basically this equality basically holds. It should be like this, and each time it doesn't hold, we're gonna plus errors, because we initialized it with 0. And if the errors is value other than 0, then we're gonna say that it's basically failed. And in the end, we need to take care of the memories that we allocated on the host and also on the device. That's the program that we are working with. And if I go to README, we need to say module load rockham. So let's copy and paste this. Let's try make. So now you see that there's a gajillion amount of warnings that they are saying that basically ignoring return value. These are warnings, first of all. You can run safely your program, which is vector add. And then you see that it says it's passed, the test is passed and it's succeeded. But all these warnings are because that we are ignoring the return value of a function declared with no discard attribute. So this means that if I go to my make file, and so right now you see that this ndebug is activated. So if I get rid of that, and if I try to compile this again, then you see there are no errors. And the reason for that is when I remove ndebug from the compilation flags, you can see it again here. When I take out that ndebug, then this is going to be the case. And if this is going to be the case, then the return value of those functions, those hip API calls, are not going to get discarded. And that is why the compiler is not throwing any warnings. So that's the first example that we can take a look at. Then we can go to basic examples, and we have here a lot of examples. So let's take a look at README of this one and see what this one is about. So it says compile and run vector addition program and use the error from error checking macro to decide how to fix the problem. To compile and run, simply say make, and that's it. So let's do make clean. I think I ran it before, I'm not sure. Make, or wait a second. There's actually a solution for this. So let's just compile the solution. And then let's just run the vector addition and see. And then we can also take a look at this vector addition.cpp and this vector addition.cpp. And you see the error here was basically, it was used HA. So this is, let me check, this is the previous one. We are, the heap mem copy, both of them are HA, which the first one should be DA. And if we go back and try to compile this one and try to run the vector addition, you see that the compiler is not complaining about anything. But while we go through runtime, then you see that it says GPU API error. And yeah, vector addition on line 76. So if you go now vector addition.cpp, then if you go to line 76, then you see that it's complaining about this. And you see that we wrapped this call into GPU check, and that GPU check is basically dumping out that error, GPU API error, da 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 da. So you see, it basically gives you the file and it gives you the line number. And that is exactly what we added here. So it gives you the file and it gives you the line number. So you see how basically easy that thing basically works. That was one example. We can go to the second one, that is add device to host data transfer. So let's take a look at README here. This one is, this example simply initializes an array of integers to 0 on the host, sends the zeros from the host array to device array, then adds 1 to each element in the kernel, then sends the ones back to the host array. However, the device to host transfer call heap mem copy is missing, and please da 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 da. So we don't care about this stuff. We're gonna go straight to the solution, and it's simply a make. So let's go to the solution and do a make. And let's run it with add 1. And you see that this example is successful. Now let's just take a look at the source code and see if anything special is going on. This is the same macro for checking the API calls, and this is the kernel function of the global ID. And what we do is that we just simply add 1 into every element of that thing. That's the size of array, the bytes, the malloc call, allocate the memory, initialize the array, and then this is the pointer for the device, the heap malloc, and then we check this, and 256 threads, and then sealing of that, launch the kernel, heap get last error for synchronous errors, heap device synchronize for asynchronous errors, and yeah, and then we basically do the mem copy. And finally, we need to free the host memory, and we also need to free the device memory. And also what we can do is to check this add1.cpp with this add1cpp, and then you see that the mistake or the to-do was basically here. There was no mistake that was happening here, but we had to basically do some stuff. Yeah, so, and that is this example. We can move on to this third example here. That's complete square elements. Let's go to solution and let's do a make clean. Let's go to square elements.cpp. So this one, oh, I remember, this is int64. So this example was previously written with int, and this wasn't basically running properly, and it was always giving the error here because of overflow on the element 65,000 something, I think. Yeah, but whatever it does is basically simply multiplying every element with itself. So it's squaring the elements, and this is the kernel function. Very simple. Yeah, you're using malloc here, initializing the array, then yeah, doing it on the device, then copy that, having 256 threads. So the program flow is quite simple and similar to what we already have seen. So let's just go with make, and then let's do the square of elements. And you see that it's success. The size is this much, blocks in the grid 4096, and threads in the block is 256. So now let's jump back. Let's go to 04. That's the complete matrix multiply. Let's go to solution, make clean, and we have matrix multiply. So this is the multiplication. So we are multiplying, let's see which one is which. We're multiplying A and B, and we're going to put the result into C. So we have columns and we have rows, and then it should be like below the indices, below the size here, n. And then we flatten the index again, n times rows plus columns. So that's flattening the indices because A and B are only sort of one-dimensional arrays. And then within this for loop, we are having row index as n times row plus I, and n times I plus column is going to be the column index. And that's how we access basically this. And after that, we simply add the C index equal the element. So yeah, that's a matrix multiplication, which we did by hand, but there are already libraries for this. So you shouldn't, if you are doing this like this simple stuff, then you should not code it yourself, but you need to use the libraries. And I think we do have later an example of that as well, and we can see the performance difference between what the code that you write yourself and whatever you run on the library. And here stuff are looking the same. We have size of the matrix basically, or size of the array, and this, allocate the memory with malloc, initialize the stuff. And the way we initialize the stuff is like j plus 1, and then the other element is 1 over the inverse of the same thing here. So if the matrix multiplication is done, then this means that so this multiplied by this is going to be 1. And since we have like 1024 elements, then you're going to sum up all those, and you're going to end up with a value of 1024. So here is heap malloc on the device, heap memcopy from host to device. Then you have your block and then threads and everything, and then you launch the kernel. Get the last error. These are the synchronous errors. Heap device synchronize for, yep, asynchronous errors, and then heap memcopy. And within this tolerance, we are going to check whether, yeah. And then I think I added this portion myself, yes, to just print out the results on the C array or C matrix. And then you need to free up the resources here. So simply let's do a make, and let's do a matrix multiply. Holy, yes, that is why we have a gajillion amount of 1024 written, because every element after the multiplication is going to be 1024. Whoops, why did I do that? I thought I was inside Vim. So that is it. Let's go to 05. We have a README here. So it says in this exercise, we'll use the matrix multiply kernel we completed in number 4 and compare its performance against the HeapBLAS version of DGEMM, or the general matrix multiplication. You need to make any code changes. You will not need to make any code changes. Instead, you will simply compile the code and submit the job. So there's nothing basically special. The only thing special is that here we have a parse output, a Python script. So let's take a look at this parse output. It's very simple lines. We import pandas, and then we have read CSV out of these results, and then certain columns which are written as ns. These are like nanoseconds. We want to convert them to milliseconds, and the conversion is happening in place to the data. So we are not creating something new. We are just replacing the values of nanoseconds with the values of milliseconds. And then, yeah, that's basically it. So let's just do, so this is the renaming. This is where the renaming happens, but the actual conversion happens here because we are dividing it by a million. And that is the difference between nanoseconds and milliseconds. That is 1e minus 9, and that is 1e minus 3. And the difference is sort of this 1e minus 6. So that's why we divide it by a million to convert it to millisecond, for average also to millisecond. So let's just see which one should we do though. Make clean. Do I need to make it, or do I need to, let's take a look at submit. So probably we need to use submit here. So let's do, or I can simply take this and do this. First I need to make it. Of course, we need to make it first. Okay, now you see that everything is working. And then, because that call, let me show it again. It uses basically RockProf, the profiling tool. And yeah, and then we have the stats, and then we have the hip trace with RockProf. These are the configurations of the profiling that we want to do. And then we run the matrix multiply. And if you, if you take a look at the code of matrix multiply, then you see that we are having the same kernel function that we wrote by hand. And then later, we are having the same thing running with heapBLAS instead. So if you go on top, here we are including also heapBLAS. So wherever you can use the library calls, that's the takeaway from this example. And this is how you call this library to calculate that matrix multiplication for you. And then we basically check the results between the code written by hand and the code from the library itself. And then if I say, for example, Python 3 parse output, then it's going to basically do that, and it's going to give me the duration. This is the matrix multiply kernel function. You see that this takes 1.4 milliseconds, on average 1.43. And then this is the one from the heapBLAS library, and it takes only 0.04. You see that the difference is huge actually between these two, the execution time. So that is the takeaway from this example, a very beautiful one. Then we have 06, that is a Hipify ping pong. Let's do a make clean. Let's take a look at README. So this is when we need to use Hipify Perl CUDA to redirect it to a new file pingpong.cpp. I can copy that. And then, yeah, sometimes, yeah, these things are not going to get always added. And then we simply need to make it. So let's remove this ping pong CPP right now, because I did it before. And the way we do this is Hipify Perl, and then we give the ping pong CUDA code, and then we put it into this ping pong CPP. And then if you do that, then you can take a look at ping pong CUDA, and pingpong.cpp to check the differences. You see that, for example, every call to CUDA error, for example, got replaced with HIP error, and CUDA success got replaced with HIP success. So this is how Hipify basically work. Like HIP malloc is the equivalent version of CUDA malloc. So now you understand how it works. But if you take a look at the CPP version, you see that we have only one include statement, this stdio, and what is being missed here is the HIP, and I think, was it HIP runtime or runtime HIP? I'm not sure. .h. So we're gonna take a look at it. It seems like it worked. Oh yeah. So now you see that this example is basically running. And the example is on its own. Do we have anything about the example? Oh yeah, it says here, this code sends data back and forth between the host and the device 50 times and calculates the bandwidth. So that's basically what it's being done in this ping pong. Yeah. We can also take a look at the code. You see that the loop count is 50, so 50 times we're going to do that. And here we have a shift to left, bitwise shift operator. It's 2 to the power of I. That's what it means here. And yeah. Then we have a warm-up loop. Yeah, and then this is the time loop where we basically do those. Yeah. Okay, and then finally it calculates the bandwidth and dumps it out. Okay, yeah, this was also a very beautiful example. And then it does it in 2 modes from host to device. You see that these are basically the times that we got and the bandwidth, that how it is basically changing up to 55 gigabytes per second. And device to host, you see that it goes up to 58 gigabyte per second. Again, don't take these values as anything. They have no meaning. Let's go to, this one has a solution. So let's see, what is this about? The memory allocations are only of size this. Okay, let's go to solution and let's make clean this. Let's take a look at matrix multiply. Oh, okay, so this is what I was talking about. So you can also use shared, and then this means that these sort of arrays are going to be shared between the threads inside a single, any particular block. And yeah, so this is the same matrix multiplication, A equals B times C, but this time they try to write it with sort of this shared arrays. And then you see the presence of some thread synchronizations here, and this is obviously important because we are using these shared values. You know, SA and SB are shared between the threads within a block, and quite certainly when we are manipulating stuff on SA and SB, we need to make sure that, because later this element relies on SA and it relies also on SB. So we need to make sure that we are synchronizing all the threads before element is going to be calculated with this access calls. So that is super, super important for us. And then after this element is getting updated, we need to make sure that we are syncing again. And the reason for that is simply this element is going to be assigned to C of index. So these synchronized threads are basically very, very important. But yeah, more or less this is the same program, but this time we are trying to use the yeah, a different approach. So the logic of the program is more or less the same. So I can say make, and then let's run this. And again, it produces the same results as 1024. Already we had it in example number 4, if I'm not mistaken. And that had also the same output. And here also it says success. So that is this example. I think that was the last one, 07, yes. So we finished these. I think this family of examples should be okay. Oh, there is one example which is like amazing. By the way, we could have also accessed these stuff in here. There's like the readmes. You can easily read them here because the markdowns are represented much better. So this was the vector add example that we solved in the beginning, and then we solved the basic examples. But in the end, it says more advanced heap make file. This is the project that is, yeah, this is the Jacobi project, which is like very, very nice. One of the very nice examples that that I've seen on this repository. I haven't checked all the examples, but this one is really, really useful. We can take a look at it quickly, maybe. So if there is anything we need to get rid of it, do we have any readmes here? Yeah, probably the readme is going to be easier if we go to Jacobi and the readme here. Yeah. And then it gives you some information how you can use it with -g giving the grid, and then with -m giving the mesh size, and -h for help. And prerequisites is that you need to have a working MPI implementation, and you need also a ROCm installation, and then simply you need to make it or use CMake to do that. And then to run it, you can use this syntax. So what we want to do is that we want to say module list. So we have only ROCm loaded, but we need to do a module available, and then we need a MPI for this. We do have a version of OpenMPI installed. So let me say module load this MPI. And now if I say module list, you see that I have both ROCm and OpenMPI, and these are the requirements, MPI and ROCm. And now I need to simply say make. And if I say make, then hopefully it's going to compile everything for me. And you see that this is a more complex sort of source file because it consists of a bunch of source files, not only one. And hopefully, do we have a Jacobi hip? Oh, we can't just simply run it. We need to use MPI run. So let's run it like that. And then you see that it says it stopped after 1,000 iterations with residue of that, 3 minus 4. And it seems like it didn't converge, but it basically hit the maximum number of iterations. That's what it seems to me, because it says it stopped after 1,000 iterations with this residue. It didn't say that it converged. It gives you also the total time spent, and it also dumps out some flops, for example, 682, and also some bandwidth, 3.86 terabytes per second. And it says percentage of MPI traffic hidden by computation is 100. Yeah. But we could also like increase this, for example, to 4. And instead we can use a grid of 2 by 2, because here you see that we have 4096 by 4096. That's the local domain size. But the global domain size is going to be like twice in this direction because we have 2 here. And then this is going to be the same. That's why we have 4096. So if I increase this to 4, it's going to be 2 and 2. So let's take a look at this. So again, every basically local domain has this 4096, but the global domain has 8192, 8192. And you see that the residual is here lower, but still it didn't converge because it says it stopped after 1000 iteration with this residual of 70 minus 5. And you see here we are considerably having a better bandwidth. It's 7.65. Previously it was 3 point something. I remember. Yeah, 3.86 terabyte per second, but here is 7.65. Okay. But I think you need to spend some time because we can't go through all the source code, but if I quickly want to show it, this is the main program that has the main logic of things. You see that it includes this header file, so that's the next file we need to check. The main, it uses MPI, so these are like for initialization, and then we have the MPI com world. Then we have grid and mesh, and then we have parse command line arguments, and then we pass in grid and mesh into that as well. And then the Jacobi, which uses grid and mesh. So we haven't initialized grid and mesh when we created them. So somewhere in this parse command line arguments, I think this grid and mesh needs to be sent by reference because here we haven't initialized them. So this function needs to change grid and mesh because this grid and mesh are going to be used with Jacobi. If you haven't initialized them, then this is going to be a problematic for Jacobi. And then we have the logic of all of the logic of this Jacobi is basically running put inside this Jacobi.run. And then after everything is done, we have, you see that the main interface is quite simple, and it should be like that too. Yeah. So first we need to check this header file, and then we need to check for this function and see whether our theory works. So let's go to Jacobi HPP, and then you see that all the required header files are in this main one. And then the grid T, you see that it's like a struct. It has these values. And then we have mesh T, also another class or another struct, and it has these values. And yeah, Jacobi T is defined as a class, and then it has a grid and mesh part of it. And then we have bunch of stuff on host, bunch of stuff on device, some timers and iterations and everything, 2 streams, computer stream and data stream. And then we have bunch of methods, which these methods are defined under private. So this means that I cannot have access through any object of Jacobi T. So this means that if I go to Jacobi main, I'm not allowed to say, for example, a Jacobi and then apply whatever, that function. I can't do that because these are like private. If I go to jacobi.hpp, because these methods are private. And the only method that is on their public is run, and that is why we have that jacobi.run, the logic of the program. It was written there. Yeah. So you can read this on your own. Yeah, but this is about like Halo Exchange, and I think I kept a slide. It should be this one. Yeah, this is like a very beautiful example. And this is just a simple representation of what do we mean with this ghost cell exchange or this halo exchange. So it is quite common in solving PDEs numerically that when we divide sort of the grid into like several regions, that every rank, for example, in MPI, this is also one of the very common examples in MPI, that every rank is responsible for a portion of the grid. Then oftentimes you're dealing with like terms For example, you have first derivative, second derivative, or whatsoever, then you need to discretize that, make it linearize. And once you discretize it, then you see that you need to have access to, for example, cells after yourself and cells before yourself, depending on the discretization accuracy you want to pick. But then if this region is being basically assigned to rank 0 and this region assigned to rank 1, then if I'm calculating stuff on this computational cell, then I need to know information from this side. But this side, you see that it's on rank 1, and I don't have access to that. That is how basically halo cells are being formed, that you have like around this surrounding of the grid that is assigned to you, you have these halo cells that they take information from um, basically here, and they put them here, they put their own information up here as the halo cells. This could be from like side to side, and for these cells down here, it could be also um, top to bottom. That's basically the idea of halo exchange. And I think this example is a solution of the Laplacian equation with this Jacobi method. Yeah. But we saw that how the code basically runs, and you can read maybe the rest of it on your own. Maybe I can also, let's take a look at input as well. Oh, this also gives like how you can use it with the grid, and also you can use the mesh, for example, with -m. Yeah. Okay, this is the parse command line arguments that we talked about. And our theory was right, because you see that this grid and this mesh are sent basically by reference. And this means that the grid and mesh are going to be somehow altered here. Yeah, so this is basically like with -g, how you need to set up the grid if the user has entered some numbers, or with -m for the mesh points, how you need to basically change the stuff according to what the user has imported there. Yeah, so this is the input is basically what is being dictated by the user of this code. Then we have halo exchange, for example. This is what is happening on, up, down, left, and right. Yeah. So the logic of this, I mean, you need to spend time. This is not, it takes some time to understand what is happening. But yeah, this is probably one of the best examples. And this is also very, very practical as well, because solving a Laplacian equation is quite common. Yeah. By the way, there's also a run all.sh, which uses this env.sh, and then we have these flags. You see that we have rocktx trace here, HSA trace, hip trace. So it seems like we are using somewhere we should use rockprof, the profiling tool. And then for every flag, it's basically exporting this, and then it's running the script in run.sh. Let's take a look at this. And quite understandably, that uses either the wrapper or it uses this MPI run call. So let's take a look at the wrapper. Okay, so here's the wrapper. This is basically the rockprof with MPI run to measure the performance. So let's take a look at this. Oh, it's just a bin bash. So what if I say, for example, run all? Or I think first I need to compile this. yeah, first we need to compile it, and then we need to say run all, and let's see what happens. Okay, so this is actually a very beautiful example, because now we also have, some statistical data um, on this program. Yeah, and it also results like, yeah, it just gives a lot of information to you that you can inspect. So yeah, you need to spend some time on the source code. Unfortunately, I don't want to like spend too much time on it right now. But that is quite possibly one of the very nice examples that you can find in this repo. Um, then that was the hip directory. So let's take a look at, I think it was hippie. So these are like one example of using, so this is like the hippie, the method for converting the CUDA code to hip. Straightforward and works with minimal modifications to source code. This example applies the hippie method to a simple vector addition problem offload to GPU using CUDA. All CUDA functions are defined in the source GPU functions.cu, and by including the hippie.h file when using the hip, all the CUDA functions will be automatically replaced with the analogous or the corresponding hip function during compile time, and then by default the program is compiled for NVIDIA GPUs or NVCC. To compile with CUDA, just run make. To compile for AMD GPUs, hipcc run make this one enabled, and note that the make file applies different GPU compilation flags while compiling for CUDA and hip. So we don't have NVIDIA GPUs here, so probably I should also go to this make file. First of all, I need to say make and clean to get rid of that. Let's go to make file and uncomment this to use hip. So let's just uncomment this and let's do a make. Okay, if you do a make, it says relocation of this against cannot be used when making a pi object. So it says recompile with -f pi or position independent executable. So I'm going to copy that. So it seems like we need to pass it as the compile parameter in here. So let's go to makefile. I need to write this example down because I need to inform. So this is hippie. I need to inform Giacomo possibly to also fix this. So this is where we, set hipcc as compiler for device. So let's go to GPU flags and add this -f position in independent executable. If I save that and if I make this, it still says, oh, now it works. I just had to clean the project first. Now it works. Okay, now if I say vector add, okay, now it perfectly works fine. Yeah, 5.26 milliseconds and this bandwidth, and validation passed and finished. Nice. Oh, actually the source code is inside the source, and you see that these are the GPU functions Q, and this is that hippie header that basically uses macros to transform these CUDA functions into HIP. And you see that within this make a script or this make file, we could switch to like with a simple flag of enable HIP, we could switch to a compilation over HIP and AMD. You can run it on AMD devices. It's as simple as that. But I need to inform them to change that line for the compilation. Then we have other examples on, some examples maybe on interoperability. Let's go to HIP OpenMP and CXX. Let's just start with this one, which is a straightforward, like OpenMP offload. Let's do a make clean and Saxby OpenMP. So we have compute 1, which basically puts the values of x to be 1. Compute 2 puts the values to be 2. Compute 3 basically does summation of all the elements on that array. And there's a check here as pass and fail. Yeah. And then within the Saxby, within the main, let's take a look. N is 1024, A is 2. We're allocating stuff with the new operator on the heap. And we have this pragma OMP target, and then we are mapping stuff. For X, we are using 2. We are copying X to the device. And then we have map to and from. But this is a OMP target data. So we still haven't done anything on the device. So this is a policy. So this is like a scoped region, and that is why we are having these curly braces here. Then we have compute 1 and compute 2. These two functions are going to run on the CPU because, as I said, this OMP target data doesn't mean anything. It just means the policy for data transfer or data exchange. And then we have pragma OMP target update. Again, nothing is happening on the device right now. We are just updating X and Y. And we are using two device, from host to device, because X and Y in compute 1 and compute 2 are getting manipulated or are getting changed. That's why we need to update them first. And then we have Saxby, which Saxby is defined down here. And you see that here is where the magic happens, where we have pragma OMP target teams distribute parallel 4. So that's basically it. So if I save this and make it, what does it say? Unrecognized command line option. Oh, that's because we are having G++ compiling this. So if you say module load AMD clang, so, and then make it again. Yeah, this should work. And then it says pass results are verified as correct. Saxby, yeah. But wait a second. So here we allocated the stuff with the new operator, but we never deallocated them. We never freed those resources. So I think this example is also, I need to inform Giacomo again. Which example was this? Let me take a look at it. This is Saxby OpenMP offload. Saxby OpenMP offload. So this example allocates memory with a new operator and it never deletes them. So here we need to say delete, and then we need to get rid of X. And you can do the same for Y as well. And let's just make. And now yeah, with Saxby OpenMP, it works. So yeah, I think this needs to be added because these two never got freed in this main function. Yeah. The rest of the stuff we don't need to care about because we are using this. Okay, so that was one example. That was simply OpenMP offload without anything, but we said we want to talk about OpenMP and HIP interoperability. So we haven't seen any interoperability yet. So let's go to Saxby OpenMP HIP. Let's take a look at this example. Let's do a make clean. Let's go to Saxby OpenMP. Let's just start with that. So you see, again, we are using the same compute functions as before. Exactly everything is similar to before. Okay, but instead of calling the Saxby function, we are calling Saxby hip. And whatever we are doing here, the same stuff we are allocating on the heap. And here we have the same story, OMP target data. Still nothing is being done. Then we are basically having target update to update X and Y after these compute 1 and compute 2. And then we are having Pragma OMP target data with use device pointer. So this is what I showed in Johanna's slide. Where was it? Thing interoperability, yeah. So this is what I was talking about. This Pragma OMP target data use device pointer X and Y, and then the Saxby hip goes inside another translation unit. So this is the first translation unit, and that was called as Saxby OpenMP.cc, and then Saxby hip basically contains the code for kernel function here, and then we have the Saxby hip here that launches the kernel. And then it also waits for the device to synchronize. Okay, so interesting. Let's go to README. You just need to module Rockham and module AMD Clang and then export this. So let's export this and then let's make it. And then it says pass results are verified as correct. But I think the same story also goes here because we allocated these stuff on heap and we never freed them. So I think here also I need to write this down as well. This needs to be a delete of X and a delete of Y. And then make clean and then make. And then we need to run this. So let me write this example as well. This is Saxby OpenMP hip. I need to inform Giacomo about this. Oops, I don't know why I do that. Another example is this hip OpenMP. Let's do a make and clean. Saxby OpenMP.cc. Okay, so now the roles are reversed, sort of, because the Saxby OpenMP is now written with OMP pragmas simply by OMP target teams distribute parallel 4, and then is device pointer. And the Saxby hip, so this is that, okay, macro for checking stuff. This is the kernel of Saxby. These are the compute functions 1, 2, and 3. And that's the size. We have, again, stuff allocated on the heap. Yeah, we have hip malloc. Yeah, and then compute 1 and compute 2. Mem copy from host to device, X and Y to device version of X and Y, and then we send these device pointers to Saxby OpenMP. Nice. And then we are having this mem copy back again from device to host. We take the device pointers and then bring copy the results into the host values. Again, one problem that I see here is again that these things are allocated on the heap and they never got freed here. So this is another problem. Although that if I say make, it should work, I think, but it's gonna have a memory leak. Yeah. So this, it says pass, but this Saxby hip, in the end, we need to say free, or no, not actually free because we didn't use malloc. So again, we need to use delete because we use the new operator, and this should be h of x, and this should be h of y. And then we need to do the same hip check and hip free, and this should be done with dx. And with dy. And let's make clean and make. Okay, you see that running is perfectly fine. I need to write this example as well. Saxby hip OpenMP. Okay, I think pretty much you get the idea. You can also follow other examples in this directory, but this was basically OpenMP and HIP interoperability. So I hope you learned something from this video. I think it was a very long video, but I hope you learned something from this video, and I hope to see you in the next one.